Welcome to Math 2318. This is section 3.3 and it's our last section on determinants. The very first thing we're looking at is they want us to use something called Kramer's rule to compute the solutions to this two equation and two unknown system. So we form matrix A, so 7, 8, 3, 8. We find the determinant of A, so 56 minus 24, and so we get 32. Kramer's rule says that the first solution, x1, is the determinant of what we get when we take the right-hand side, the B, and put it in the first column. The second column is the original second column of matrix A. And then we divide that by the determinant of A that we just calculated. So the determinant for the top would be 24 minus 120. And so we get minus 96 over 32. And we get minus 3 for our first solution. To get the second solution, we put the B in the second column and redo that 2 by 2 determinant. And so we get 7 times 40 minus 8 times 3. So 256 over 32, and we get 8. So, and that gives us our two solutions. So in general, so long as the determinant of A is not 0, to form the xi solution, I simply take the B and run it down the ith column. And then you calculate whatever that determinant is. 3 by 3, 4 by 4, 10 by 10, whatever it happens to be. And that's Kramer's rule. All right, in question 2, we'd like to form something called the adjugate of the given matrix. So here's matrix A. Remember that when we did the determinant, each position had signs that went with it. And so that was minus 1 to the I plus j. So plus, minus, and so on. The adjugate of matrix A is, so C11, C12, C13, different than the normal way I would label it. Well, what is this C11? C11 is what the determinant I would get by going to the first position here, covering up the column and row it's in, and so I get this cofactor 1 minus 1, 1, and 5. So I form that determinant, which is just a 2 by 2, which is easy, and I get 6. 6, because the position is plus, stays 6. What about the C12 position? Well, I cover up the 1, 2 position, so here and there. So I get 2 minus 1, 0, 5. All right, so I get 10 minus 0, which is 10. But because that's in the minus position, it's a minus 10. Moreover, when I put this in my adjugate matrix, it's going to go down the first column. C13, how do I get that? I go to the first row, third column, cover that up. I get this cofactor 2101. I calculate, so 2 minus 0, and I get 2. But let's see, the 1, 3 position is plus, so it would be a plus 2. Just a few more. What about 2, 1? 2, 1, so 2, 1 is this position. All right, so cover up the row column. I get 2, 3, 1, 5. And so I get 10 minus 3, which is 7. But the 2, 1 position is minus. Therefore, I get a minus 7. So you continue doing this for C2, 2, 2, 3, 3, 1, and so on. And then you arrange them in this particular pattern. And so we get that the adjugate of A would look like this. They want us to find A inverse using the adjugate. And the adjugate is simply 1 over the determinant of my original matrix. So that's not 0. And I multiply that by the adjugate. So to get the determinant of A, let's see, back up here to look at A, I'm coming down the first column because I've got a 1 and a 0, making that pretty easy. I could have also picked the last row, but I picked the first column. So that'd be 1 times this cofactor minus 2 times its cofactor. And so by doing that, I ended up with a minus 8. And so I simply take my adjugate, which you see here, and divide each of the terms by minus 8. Some of these I could reduce, I just didn't reduce them. Okay. In question 3, they want us to use our determinants to find the area of a parallelogram. So I took my coordinates and I plotted the way that the parallelogram would look. Now, I form from the origin out here to 2, 6, that's one side. Essentially that's B1. And then from 0 out to 6, 4, that's B2. So here they are listed there. Now, if all the points here were away from the origin someplace, I would need to shift the closest point back to the origin and then calculate to get B1 and B2. And so it turns out that the area of the parallelogram is the absolute value of the determinant of A. Well, let's see, what's that? That's 8 minus 36, so absolute value of minus 28, which is B positive 28 with absolute value. Another way, rather than shifting them back, is if we have a parallelogram here, and this is 4, 5, 6, 8, I could form the vector going from 4, 5 to 6, 8 simply by taking 6 minus 4, 8 minus 5, and I get B1 is 2, 3. And here I could take 10 minus 4 is 6, 7 minus 5 is 2, and that would give me my columns without having to do any shifting. So another possible way to do this. All right, in question 4, we are given two sides of a parallelogram, minus 5, 7 and minus 5, 10. So I've drawn them here in the plane. So here's my parallelogram. They're going to get mapped by matrix A. So here's matrix A. And they're going to go someplace new. And so I wanted to figure out the area in two different ways. The first way, I took A and I applied it to both B1 and B2 just to see where did it go. So what happened to minus 5, 7? Well, it went to minus 66, 81. And minus 5, 10 went to minus 90, 105. So I actually have my new B1 and B2. And so I calculated the area there of the image where it went to. And so it's minus 6,930 minus a minus 7,290, and I get 360. And that's the area of the image. Now we have a formula in the book that says the area of the image is simply the absolute value of the determinant of the original matrix A, multiplied that by the area of the original. Okay, so well, what was the determinant of A? 2 times 8 is 16 minus 40. That's in absolute value. So I get the absolute value of minus 24, which is 24. So got that. And what about the area of the original? Well, I put in my original B1 and B2. So I get a minus 50 minus a minus 35. All right, so in absolute value, that's 15, and 24 times 15 is 360. So it's exactly the same as I got by finding actually what did A do to B1 and B2, and then find the new area of the new image. But either way, you get exactly the same number. So that concludes our chapter on determinants.